Our topic is about simplified sample preparation HPLC analysis of Ergovaline in Fescue. So hi, my name is Kasih Aina Shazana binti Muhammad Nazri, and now I will present about the introduction. So the introduction is about the interest in the endophytic fungus with Acremonium coenephalum and its symbiotic relationship with tall fescue, which is Festuca aeruginosa, that has emphasized the need for reliable and efficient method to analyze ergovaline, a key compound linked to this interaction. A simplified preparation method has been developed, which is involving alkaline chloroform extraction, silica gel column purification, and HPLC with fluorescent detection. This method improved recovery rate for ergovaline and internal standard with 93 and 94% respectively, while reducing variability compared to older techniques. It also allowed analysis of 60 to 80 samples daily and demonstrate high reproducibility between laboratories, accounting for 97% of variability in result.
Hi, my name is Anna Najiha, and here is the objective of this experiment. The first one is to explain the importance of ergovaline analysis in fescue for managing fescue toxicosis. And the second objective is to show the development and advantages of the simplified sample preparation method for HPLC analysis. And the last objective is to highlight the method's improved efficiency, accuracy, and inter-laboratory repeatability.
Now we move to the methodology. The first one is sample collections. 16 endophyte infected tall fescue genotype were grown in 15 cm pot in the greenhouse with daily watering and weekly fertilization using a commercial greenhouse fertilizer. Harvested plant tissue was freeze-dried and ground to pass a 1 mm screen in a cyclone-type mill. Plant tissue from each genotype was analyzed for ergovaline concentration by a previously published method, and tissues of the 60 plant genotype were mixed with each harvest date by assigning them to class of high, medium, or low ergovaline content. Second one is ergovaline analysis, extraction and purification of sample. A simplified procedure was tested by selecting 3 1-gram subsample, each of the low, medium, and high ergovaline plant tissue and extracting them with chloroform as with the Rottinghaus procedure. 20 ml of plant extract were applied to a solid phase chromatography column, which consists of a 1 cm Wetman 41 filter paper disc in the bottom of a 3 ml disposable shrink barrel, followed by a 1.0 cm silica gel HL pad, a 1 cm Wetman 41 liter disc, a 1 gram Na2SO4, another 1 cm Wetman 41 filter disc. The roto evaporation step was eliminated and disposable nylon 66 filter were fitted to the bottom of the shrink barrel of the solid phase column. After eluting pigment from the column with 5 ml acetone chloroform, residual acetone chloroform was removed from the column with 1 ml ethyl ether, and the column was eluted by slowly plunging 2 ml methanol using the plunger manufactured for the shrink. The final volume of the methanol eluate was adjusted to 2 ml by adding 0.1 ml methanol and injecting directly into the HPLC. The third one is ergovaline analysis, liquid chromatography. Samples were examined for ergovaline using the HPLC method described by Rottinghaus. Standard solution ergotamine and ergovaline will prepare in methanol and store at -10 degrees Celsius. Working standard solution ranging from 50 to 500 nanogram per milliliter will prepare in methanol. Analyses were conducted using a Shimazu model LC600 liquid chromatograph equipped with SIL9A auto-injector and NRF535 fluorescent spectrophotometer.
So now I will explain about the methodology of statistical design and ergotamine and ergovaline recovery. For statistical design, a split plot treatment assignment was used with the ergovaline extraction method as the main plot and ergovaline level of the sample randomly assigned as the subplot. 3 subsamples were analysed per sample and samples from different dates were used as replicate in time. Samples were analysed within each harvest date immediately after freeze drying to prevent loss of ergovaline during storage. Statistical analysis was conducted using the ProGLM procedure of PCSAS. Mean value for both methods were tested for similarity using the paired t-test within each class of plant sample. So for ergotamine and ergovaline recovery, ergotamine recovery was determined from the internal standard of each endophyte infected tall fescue sample analysed for ergovaline. Ergovaline recovery was determined for each procedure by adding 1 ml of methanol containing 860 nanogram milliliter of purified ergovaline to 1 gram sample of freeze-dried endophyte-free tall fescue. 6 samples were prepared, extracted with chloroform, and purified of the silica gel chromatography column as described for each procedure.
So, I'll be discussing the result of our ergovaline analysis using the simplified sample preparation method. Let's take a closer look at the result and connect them to our discussion. Here, we have a graph showing the regression analysis of ergovaline concentration measured by 2 independent laboratories, one in Georgia and one in Missouri. Both labs use the simplified method. The data points are closely aligned with the regression line, which has the equation y equals to 31 plus 0.86x and coefficient determination R square value of 0.97. In experiment 1, simplified sample preparation of endophyte infected tall fescue tissue. So firstly, in comparison of chromatography column size, the larger solid phase chromatography column of the Rottinghaus et al. 1991 procedure required 8 ml methanol to elute ergovaline and required rotor evaporation to concentrate ergovaline for analysis. Reducing the solid phase chromatography column size required only 2 ml methanol for elution of ergovaline and permitted direct injection into the HPLC. Next, variability in ergovaline value. Ergovaline value were not different between procedures, but the data were more variable in fescue sample analyzed by the rotor evaporation method Rottinghaus et al. 1991, with variability increasing as the ergovaline content increased within the samples. Variability of the data was constant using the simplified method, regardless of the ergovaline content within the samples. More consistent results produced by the simplified method can be attributed to the omission of the rotor evaporation step because 1. Ergovaline apparently sorbs to glass when taken to near dryness following rotor evaporation, and rotor evaporation to a constant near dryness is difficult and subjective. And last but not least, recovery rates. Recovery of alkaloids using the Rottinghaus et al. Procedure averaged 82% in the range of 79 to 84%. For ergovaline, an average 83% in range of 79 to 86 for ergotamine. These results were similar to Rottinghaus et al., which is the recovery of alkaloids from the simplified procedure average 93%, range 89 to 95% for ergovaline, and average 84% range 93 to 96 for ergotamine. Reducing their column size eliminated the need for rotor evaporation, thus increasing accuracy and laboratory throughput from 18 to between 60 and 80 samples per day.
Now I will talk about the result for second experiment, which is experiment interlaboratory repeatability of the simplified sample preparation procedure. The correlation between laboratories. The ergovaline level measured in tall fescue straw sampled by the Georgia and Missouri laboratories show a strong correlation as indicated by the regression analysis. This demonstrated that the simplified sample preparation procedure yield consistent results across different laboratories. The Georgia laboratory reported slightly higher values for samples with low Ergovaline level and slightly lower value for other samples. The slight bias is reflected in the slope of 0.86 and an intercept of 31 microgram per kg in the regression equation. For this experiment, it have high recovery rate, which is the recovery of the internal standard Agustono exceeded 94% in both laboratories, indicating the method's high accuracy and reliability.